Everyone, welcome to a new class. This one is going to be a bit different because it's going to be just myself. And the idea is that I think is better that from now on I will just prepare classes, very short ones, just myself, and then I will share them with you through YouTube and also through the mail. So then in that sense I can prepare classes that are short and they are based on your comments or questions. So I think I hope you like this new way of learning about DeSIRe and inversions. Okay, so then today is going to be related to preparing initial atmospheres. So the idea is that we are going to combine 1D semi-empirical models that are available in the literature. So you can download them or you can copy them from the papers. And we are going to select a set of models that cover different physical scenarios. So it could be a reference white sun atmosphere, or it could be a sunspot model. Okay, so then the idea is that we are going to initialize the inversion with different atmospheres. So then the code has more variety of scenarios to get a better fit. Okay, and to change the initial conditions so it can get a good solution. Okay, so then that's a copy of the official publications that we are going to use in today's folder, but as a reference I put them below. So it's the HSRA atmosphere from 1971, so it's an old one, but I think it's a very good one. Then there's a Val-C model that is from Vernasa et al. 1981. Then we have I think people call it MACEL because it's the acronym of all the first author, of all of the authors of the paper, but it's from Maltby, 1986. This is a sunspot model. And then we have different FAL models that they are also acronym of the author's name, from Fontella, Jean Avret, and I don't remember, but you can check it. And we have that as a very famous initial publication from 1993. That is where the initial FAL-C model that we have been using in class was published. But then they also released a new version of all these models and more comprehensive computations, mainly from the UV background and other terms, in 2006. So these are the ones that we are going to use today. So the process we're going to follow consists in 2 steps. First, we're going to take the atmospheres as they are in different formats and different scales. So the first thing we want to do is to interpolate them to a uniform optical depth. And it should be the same for all the atmospheres because we are going to run the inversions using them as initial conditions. So then they have to cover, at least they have to have the same dimension, but ideally it's better if you just also have the same optical depth range. And these can be modified, so I will propose one that is based on covering enough height to synthesize and invert chromospheric lines, but also a given set of values that will allow us to have a wide range of nodes. But in principle, you can change it at any time. Okay? And then the second step is that we have the atmospheres that basically most of them are mainly temperature and thermal parameters, but there's no information of sometimes velocity or magnetic field. So then we are going to create a library of atmospheres that is based on the previous ones, but adding different combinations of magnetic field, line of sight velocity, and other parameters. Okay? So then there's no miscellaneous today, and later on I will go to homework. Okay, so then the idea is that this folder is the one that you will have when you study this class. And the idea is that you have inside, let's put it this way, so you have input, and these are the outputs, and these are the references. So here are the papers that I mentioned before in case you want to check them. And then we are going to start with this ideal program, and then we are going to use the second one. Okay, so there's inter because we are going to interpolate the atmosphere, is a program that sorry, it will read the atmospheres. So I put here again the names, and also in the case of the FAL atmospheres, we have different models. So we have, like, for example, C means quiet sun, H means splash, P is for facula, R is for penumbra, S sunspot. So we have in general a big variety of models. Okay, so then the models are already on DeSIRE format because Basilio adapted them in the past. So we are going to use IDL routines, the normal ones, so the read model and the write model for reading them. So in this class we are still using IDL, but hopefully in the future we are going to prepare similar Python routines to do the same example. Okay, so then we read, the atmospheres are in input in this folder. We can see that they are here. Okay, so then we read them, and then we are going to interpolate them to optical depth scale that has 81 points, and it goes from -6.8 log tau to 1.2, sorry, to 1.2. And then the idea is that I think this is large enough to cover most of the chromospheric lines and photospheric lines that we are targeting to analyze with DeSIRE. And also having 81 points means that when we are doing the inversion, we can select all this range of nodes. So in principle, I think 1, 2, 3, 5, 6 is usually the normal criteria. But in principle, you can go to 9 maybe, or sometimes 11 if you have a lot of spectral points. But the good thing is that you can slowly jump. So 1, 2, 3, and then 5 is a slow pace jump in each iteration. So that's, I think, is very good. But as I said, if you prefer to have a different range, you can always change it. And the important thing is that try to have points, a number of optical depth points that will allow you to select a very large number of nodes for the time you do the inversions. Okay, so then the process is simple. We have the original, so we are reading here the atmospheric parameters, and this is the original optical depth, and we are creating a new one. So this is a uniform one. This one, I don't know, sometimes it could be uniform, sometimes not, but for us it's not a big problem. And we just run the IDL routine interpol, that is for interpolation. And for example, in the case of temperature, we just provide temperature, the original optical depth, and the new one. Okay, and then with this, we are interpolating all the atmospheric parameters. Here, it may happen that the atmosphere that you are selecting is not reaching log tau -6.8. Imagine that it reaches -6. If this happens, it's not a big problem, because in this case, it is true that we are not doing an interpolation, we are doing probably an extrapolation, if we can say it in this way. But the important thing is that the atmospheres, so the spectral lines at upper layers, they are not extremely sensitive to the atmosphere. So if remember the response functions of calcium, it usually drops below -6. So then if the atmosphere is not extremely accurate there, it's not so important for the spectral line, but also you have to remember that the code will run first time with that atmosphere, it will generate a profile, but then just after that it will start changing the atmosphere. And as soon as you have two nodes, it will change the extreme node in the top part. So then it means that even if your atmosphere is not so realistic, the code is going to change it just after the first or the second cycle. So it doesn't matter if you are maybe artificially expanding the atmosphere, it's okay. For this scenario, it is fine. The important thing is that I think for consistency, it's good to have a set of atmospheres that they have the same dimension and also the same extension. So then it's good to later on check why certain atmospheres behave better, and then maybe select ones to put early on the inversion and then move other atmospheres too late in the inversions, so then you can speed up the inversions. I will explain this maybe later a bit better. Okay, but the important thing is we just interpolate to a uniform grid. It doesn't matter if the atmosphere the original atmosphere doesn't reach high enough. For us, it's fine. And then one thing that I recommend you, even if we are going to change it later, I think it's good to do it here just in case, and is to give very, very, very small values to all the atmospheric parameters that you may eventually invert. So then even if they are close to zero, so I mean, if they are close to zero, they will not affect the profile synthesis, for example. But so if you don't invert them, but if suddenly you decide to invert, for example, microturbulence or microturbulence, so if the atmospheric parameters is 0, the code cannot invert them because the perturbations the code apply on each atmospheric parameters are multiplicative perturbation. So if it is completely 0, then something multiplied by 0 is always going to be 0. But if it's something like 1 × 10⁻⁴, for example here as you see in the microturbulence, then the code can change it and eventually make it larger, like 1 kilometer, 2 kilometers. So then my recommendation is something very small for microturbulence. So this is kilometers per second. So this will be like 10 centimeters. And we are doing the same here for the microturbulence. So it's 1 centimeter per second. In the case of the field strength is 0.1 Gauss. So this is really, really small. Velocity again 1 centimeter per second. So this is negligible. And then inclination is 0.1 and azimuth 0.1 degrees. That is really, really, really small. But the important thing is that if you just pick this atmosphere and you said, I want to invert the inclination, then the code will do it. But if it's 0, then the code will not change it and it will always be 0. Okay, so this is important here. Even if later we are going to change the atmospheres and put more values here and different ones, it's important, I think, as, to have something that is not 0 in all of them. Okay. And then when we just define this, then we write the atmosphere, the interpolated one, and with non-zero values in all of the atmospheric parameters in output. Okay, so we started working from input. Okay, now we are saving in output all the interpolated atmospheres, and the process is the same for all the atmospheres. So now we are reading file F, we define the optical depth, we interpolate all the atmospheric parameters, and then we defined very, very, very small values for all the atmospheric parameters. And then we just save it with the different name. So now we are going to do the same for the file H, file P is exactly the same, file R, file S, HSRA, MACL, and then val C. I think this is the last one. Okay, so then we have read all the atmospheres, we have interpolated them to the exactly same optical depth range, and then we assigned to all the atmospheric parameters that are usually the ones we embed non-zero values. Okay, so until this point, I think we have a very good reference, but my recommendation is to go a bit further and put values that are different to the atmospheric parameters, in the sense that we are going to create a library with a wide sample, wide variety of samples, so then the code can I think better fit the profiles. So let's go to the program and then I will show you one example at the end. Okay, so then in this case is what I was saying. So we are going to, just let me show you here and then I will explain what we are doing. So we are reading now from output. We are reading, for example, the FALSI model. And then we are going to change the atmospheric parameters. So microturbulence, for example, I'm adding 1 kilometer per second, 200 Gauss, plus 1 kilometer per second for the line of sight velocity, 10 degrees for inclination, and 70 degrees for azimuth. And then we are going to do this in a different way for different atmospheres. And then we are going to save them with this name. That is the one the parallel wrap is looking for when doing inversions both in SER and DeSIRe. Okay, and the code will always start in order. So if you defined an atmosphere that is starting from file C, and you define it as atmosphere clustering, this is the CL number 1, then you are assuming that your inversions are going to start from file C. If you want to have a different atmosphere, for example, HSRA or a file P, then you should, as the first atmosphere, then you should change here this. But in my case, I'm choosing very wide range of atmospheres. So here, so then we are going to make a big sample, I think it's 12 in this case, of different atmospheres from FAL, HSRA, MACL, so it's very varied. But if you want to have, for example, that your first atmosphere is a penumbra or an umbra model, because you are inverting a sunspot and you are focusing on the central part of the region, then it's better to change the order and maybe start here with a file S or a file R. Okay, but I think this is, for now, you just try. I recommend you to try it how it is now, and then you can experiment this a bit later. But the important thing that this is the one that I was describing in this paragraph. If you see these values, for example, you see here 200 for the magnetic field. So the atmosphere, the initial one is file C in both cases. So you see 200 here and then 1000 here for magnetic field, and you said, why are you doing this? And and the idea is that I think there's no strict rule of which values you need to include, but my recommendation is pick different values that cover a wide variety of spectral profiles. So having a weak a magnetic field and a strong magnetic field will make very different Stokes I profiles, very different Stokes V profiles. Having inclination that is below 90 degrees and above 90 degrees will make that your profiles, for example, Stokes V, will have an opposite polarity. So, for example, in this case, I'm choosing an almost vertical magnetic field of 10 Gauss, but this one is above 90. So if you check the Stokes V profiles that you generate with this inclination and with this inclination, they have opposite polarity. So then you are allowing the code to start from asynthetic profiles that could be very close to the one you have because the polarity is maybe positive, or it could be very far from the one you have, so the polarity is very different, or is the opposite one. But then you are having both options, so it's very easy to the code to check one, and if it doesn't work for any reason, then check the second one, and it said, oh, now I'm getting very close to the profile that I want to fit, so then things become much more smoother. So then the recommendation is cover positive and negative velocities, low velocities, high velocities, weak and strong field strength, and then inclinations that go below 90, above 90, maybe close to 90, maybe very vertical. I mean, like 0 or close to 0 and close to 180. And also the azimuth the same. So the azimuth is a bit more complex because we have the ambiguity, but you can try like 30, 70, 120, 150. So these combinations that will allow the code to just start from different Q and U profiles. And then in my case, I usually, because in general, except in specific situations, you will have that, you always have quiescent. So then I always like to start from FAL or HSRA models initially, because even if you are getting to strong magnetic fields, usually the temperature from the FAL models is, or HSRA models, is relatively smooth. So it's easy for the code to change it and then get a good solution. So for me, I always try to start with a quiescent model like FAL C, and here you have the opposite behavior. So weak and strong field, opposite velocities. So this is +1, this is -2, and then opposite polarities for Stokes V. Okay. Then I add different combinations. So in my case, I still want to have more quiescent models. So I have an additional 2 DeSIRe atmospheres that again, this is weaker, this is stronger field, this is minus velocity, this is positive velocity, so negative and positive. This is 13 degrees, this is 170, so they are still opposite combinations of line of sight component of the magnetic field and the velocity. And we are changing the temperature at the same time because it's a different atmosphere. So we are providing the code a lot of options to just from the beginning to have a different synthetic profiles. And then here I just recommend you to try. I tried in this example to just cover a lot of scenarios. So file H, file P, file R. I tried to keep it relatively reasonable in the sense that file R, it's a penumbra model, so I tried to get inclination relatively close to 90. The field strength is large. Velocities are not so large, but it depends, of course, in the region of the penumbra. And then in the case of the sunspot atmosphere, I put it a very strong field. I put it vertical. It could be 175, or I mean, it could be close to 180 or the opposite. So here you can play a bit, but in general, one expects that in the umbra the fields are relatively vertical and really strong. So here it's just to try to have it consistent, but again, the code will change it as soon as you start the inversion. It will change it. And then a val model, again 2 combinations, and then the Mackel, that is again sunspot, and then the file F atmosphere. So then with this you can have 12 atmospheres that are very different, not only in line of sight, magnetic field and velocity, but also in the temperature and the thermal part. So I think this will allow the code to really experiment if you are allowing the inversion to use as up to 12 initial atmospheres. Okay, so I hope this was helpful, and I just want to show you the impact of using 1 and 12 atmospheres on a specific scenario. But just let me revise that I said all I wanted to say. So we interpolated atmospheres, we added a constant value with height, this is what we said. We used different input atmosphere, so then the code has a very wide range of initial options. So then the synthetic profile, the first one that it will generate is going to be very different from one atmosphere to the other. And then inside, yes, so then let's go to HD figures because there I put an example. So this is, let's make it bigger so then you can see it. So maybe too much. So then here you have, I'm sorry. So here you have the chi-square values that are produced from an inversion. It's an observation, it's a complex one. So this is a relatively complex scenario. And I just ran the inversion with the same configuration, except changing the number of initial atmospheres, and are the ones that we have here. So then in the first case, I use 1 atmosphere that is based on the file C model that we saw before. And then in the second case is the complete range of atmospheres that we created. So it's from file C, file H, file P, file R. Okay, so then what we have here is that the chi-square values, here is representative one based on difference on the Stokes I. In general, it's close to 1, that in this context means that is very good. We have gray areas, but in general, white is the dominant color in both cases. But you also have regions that are dark or very, very dark. And then this means that either the chi-square is very small, so it means that the fit is not good, or even 0, that it means that the code, for any reason, it was not able with 1 atmosphere to get a reasonable fit, and maybe it just didn't have any solution. However, in the case of 12 atmospheres, you start to see that all those isolated black dots, like the ones that you see here, they have disappeared here. And then you have that all the dark big patches, like this one, it's much smaller here. This one that also was very big, now is much smaller. Here there was like a trend of some points, so always providing very bad fits, and here is almost not detected. And then this one, it's still present here, but it's much smaller. So then just changing, so adding more atmosphere, so allowing the code to start from a different value of the chi-square, because the polarities are different, the amplitude of the Stokes V is different, because velocities are also different. So just allowing the code to play more, you improve a lot the inversions. So not only everything is a bit whiter here, it's just that most of the bad pixels that you have before, they have disappeared. So for this reason, I recommend you the first time play with the inversion configuration to achieve the upper panel, because if I see it, I said it's good. So most of the things are white, but there are some bad pixels. But as I always recommend, you try with one atmosphere, reference one, maybe a quite some model, but try with one atmosphere until you get a number of nodes and a number of cycles and everything that looks reasonable. But after that, be ready to run it with more atmospheres, because it really improves a lot. And as you can see here, I think it's very clear to see that improvement. So yeah, and then as a final comment, it's true that there's dark patches here, and in my case, for example, I'm working on this, and I think we may need to improve a bit the configuration of the inversion, maybe with more nodes, or maybe changing something else, because ideally you want to have all your pixels with reasonably good fit, and maybe those pixels are very complex for any reason, so maybe we need to start even from a more complex atmosphere, maybe with gradients or other elements. But the idea is that you at least want to have that only maybe 1 or 2% of your pixels are bad, the rest of the pixels should be very good. Okay, so then I think this is all what I wanted to say here. Yes, you can read this later, and then just let me go back to the presentation. So then as a homework, I just want to ask you if you can try to understand the different steps that we followed today. I think it's very important that you verify that the spectral lines that you are going to use, they form, or they are mostly sensitive to the atmospheric parameters in the optical depth range that we selected. So for example, if you are going to work only with photospheric lines, then you can cut the optical depth scale, maybe to log tau minus 4.5 or something like that. If you are going to work with calcium, infrared, with potassium 1, magnesium 1b, so all these upper photospheric chromospheric lines, this atmosphere is completely fine. But if you are going to work with lines that form much higher, so I imagine magnesium 2 H and K, or maybe calcium 2 H and K, I think still minus 6.8, so log tau minus 6.8 should be fine, but I would tend to try at least and compute some response function, some general one, because maybe you need to extend to maybe log tau minus 8 or something like that. So it's always good to, when creating the set of atmospheres, to be sure that lines that you're going to analyze, they form in the optical depth range that you have defined. So in this case, we have enough for all the atmospheric, or the photospheric and chromospheric lines that we usually use. But just in case, as a warning, just double check that. And then I think it's also good if you experiment a bit with initial atmospheres. I selected 12 and reference one, and based on my criteria that usually simple, quite sound models is the best for starting the inversion, because the code then can change nodes and make it much more complex. But maybe you want to try to add a bit more complex one, or to add a large number. So imagine 5 combination of FAL-C, 5 combination of HSRA, 5 combination of FAL-P. So maybe the library grows up to 40 or 50 atmospheres. I think that's perfect, and probably it should be even smoother than what I showed when using 12, but it's always a matter of time. So usually if you get good results with 1 atmosphere, going to 12, for example, it doesn't mean that you are 12 times slower. It's usually like 2 or 3 times, because some pixels will just be well fitted with 1 or 2, and only just a few pixels need to go to 12. But it still is a jump a few times. So if you go to 50, probably it would be equivalent to embed the map like 10 times or 15 times. So just be aware of that. Maybe you can go in a step-by-step process. So maybe play with all the atmospheric parameters and an inversion configuration with 1 atmosphere. Then when you're happy, just maybe use 10. And then if it still looks that you may want to improve it a bit, then you go to 50. But don't try it the first time, because then you will be waiting like 1 month to get the first results, and then you realize that something went wrong. So it's good to just leave it to the end. But if you want to choose 10 or 50, I think both options are fine. Okay, and then next class is, I think this is going to be a dynamic process. So I don't have a date, but I have idea that what I want to tell you in the next class, and it will be a detailed process using an example from SST data from Chris, how to take the data, to normalize the data, to make it to make the spectral range uniform, how to eliminate points that they were not present in the original data after this interpolation, and then also calibrate the continuum based on the heliocentric angle, and then just prepare everything for doing the inversions. And I think this will be very generic, so everyone that has SST data and wants to prepare it and invert it with DeSIRe, this will be almost the same method, changing just minor things. So I want to do this, and hopefully it will be soon, maybe in a few weeks. But for now, I just want to say thanks for watching this video, if you watch it anytime. And as it's Friday when I'm recording it, I just want you to wish you to enjoy the weekend, and I hope to see you soon. Okay? Bye!